Good evening. We'll continue discussing questions that we discussed yesterday. I think there is some portion I discussed yesterday, so I'll continue for some time the question discussions and then discuss the other topic. So in 1D convolution, an input 12103 is convolved with zero point 0.5, zero point 0.2 kernel. There is no padding. The stride is 1. What is the first output value? Yeah, so stride 1 will be the kernel slides one step at a time. So the first output will be the from the 1 to 1 0 3. We take the first two inputs. This is what the kernel will be converted on. So 0 0.5, 0 0.2. So 1 into 0 0.5 plus 2 into 0 0.2. So it will be 0.2. So using the same output and kernel, what is the second output value? The stride is 1. Yeah. So it is 1, 2, 1, 0, 3. So when the stride is 1, it will move only one step. So it will take these two and then multiply with 0.5 and 0.2. So it will be 2 into 0.5 plus 1 into 0.2, which is 1.2. For a 1D convolution, with input length I is equal to 5 and length k is equal to 2. This one 5 striding is 2. The output length is three, 6. For 1D convolution with input length I is equal to 5 and kernel length k is equal to 2. No padding, stride is 1. The output length is A5, B4, C3, B6. I'm not sure about the question. Is stride is normal sliding? Uh, can you rephrase it? I'm not sure what you're asking. No, this I have mentioned here in the question that stride is 1. That is why it's normally not 1. You can specify whatever value. But here in the question I have mentioned that it is stride 1. So the output length is given by the input length minus the kernel length plus 1, which is 5 minus 2 plus 1. So that is 4. It will be the same. So I don't know what you mean by without stride. It's 1. So here we have mentioned stride is equal to 1. The stride is how much you move. So you can't do any convolution without moving anything. So here each stride is 1, and if I have 1, 2, 1, 0, 3, you take this 2 first, then this 2 first, then this 2 first, next, and this 2. So you get 4 output. This is output 1, this is output 2, this is output 3, this is output 4. That is why you get this 4. So it will differ if you use a stride, another stride value. So that is the one. The stride is how much, like what is the next step size that you take in convolution. What is the formula for the signal activation function? It is max of 0 comma x, sigmoid of x is 1 by 1 plus e raised to minus x, e raised to x minus e raised to minus x by e raised to x plus e raised to minus x, x. It is 1 by 1 plus e raised to minus x. The output range of tan activation function is 0, 1, minus 1, 1, 0, infinity, minus infinity, infinity. Tan H output values are between -1 to 1 and it is centered around 0. So the answer is -1 to 1. The derivative of sigmoid function is 1 minus tan h cube of x sigma into 1 minus sigma 1 if x is greater than 0. The e raised to minus x by 1 plus e raised to minus. It is sigmoid into 1 minus sigma. Which activation function has an output range of 0 to infinity? Sigmoid, tan h, ReLU, none of the above. Yeah. For sigmoid, it is 0 to 1. Tan h, it is -1 to 1. And for ReLU, it is 0 to infinity. What is zero padding in the context of CNN? Removing border pixels from the input, setting the values of all added border pixels to zero, setting padded pixel to value of the nearest edge pixel, randomly shuffling border pixels. Check. So this is setting the values of all added border pixel to zero. So this zero padding will add a border of zero value pixel around the input image. So you can control the size of the output that you want. This is one of the reasons why we use this zero padding. Without padding, repeated convolution causes the feature map to grow in size, stay the same size, shrink in size, become deeper. So each this convolution will reduce the spatial dimension, and after many layers, it will be very small. The feature map can be very small. So padding is one way to prevent this. So it is shrinking size. What is the primary function of a pooling layer? It lacks nonlinearity, it reduces the spatial size of feature map and provides translation invariance. It increases the number of feature maps, connects all the neurons. Yes, it will reduce the spatial size of the feature map and provide translation invariance. So it does this downsampling operation, and also whenever there is a small shift in the input, because of pooling, we get the same, it will be the same pool output. So the result, it will provide the translation invariance. So it is 6. So the maximum value is 6 here. The vanishing gradient problem in the network refers to gradients becoming too large during backpropagation. Gradients becoming very small as they propagate backward, making early layer weights barely update. Activation function causes output explosion. Feature map explode to higher value. So during backpropagation, the gradients will be multiplied across the layer, and if this multiplication involves a value that is less than 1, the gradient will shrink exponentially as it propagates backwards. So early layers, it will receive nearly zero gradient update and learn extremely slow. So that is the vanishing gradient problem. Vanishing gradient problem is usually observed in very deep network because usually in very deep network only when the gradients are multiplied across the layer, the gradients will shrink as it reaches the initial or the early layers. So this is something that is usually observed in all types of deep neural networks. ResNet introduces the connection. What problems do they solve? Overfitting in shallow networks, vanishing gradients by allowing gradients flow directly, translational invariance, reducing the number of parameters in dense layer. So ResNet does not reduce the number of parameters in the dense layer, but it helps in allowing the gradients flow through identifying the shortcuts by introducing this skip connection. So it solves the problem of vanishing gradient. So deep networks includes so artificial neural network is the first thing that we discussed, and uh, so this is not all the deep all the deep networks are artificial neural networks, but not all the artificial neural networks are deep networks. So artificial neural network will not have multiple hidden layers. It's like an umbrella term for all these the deep neural networks. But deep neural network is when there is more than one hidden layer. So deep networks, so mainly these networks have vanishing gradient issue when there are a lot of layers. So like in one of the weeks, there was a discussion about different architecture like ResNet, InceptionNet, TenseNet, etc. So all those are deep architecture. They have many layers. And when they have many layers, the gradients are, when it comes to the early layers, it might become very small value. So at that time, the weights will not get updated because the gradient value is almost equal to zero or very small. So that is what the gradient, vanishing gradient issue is, and that happens in mainly this deep neural network. Coming to translational invariance means if you have something in an image, for example, you have a image with a red color roses. So if that red color rose is either in the top left corner or in the top right corner or in the center or wherever it is, if you do max pooling operation, it will give the same output because it is trying to summarize what content is there within that block. So, irrespective of the location of the content in the block, it will give the same output. That is what is translational invariance. So what is the defining characteristic of semantic segmentation? Each object instance is assigned a unique label. Every pixel is assigned a class label, but all the instances of the same class share that label. Only the bounding boxes of objects are predicted. A single class label is assigned to the entire image. So semantic segmentation will classify every pixel into a category. But whatever category that is, it will treat all the instances of that same category as one class. So if there are five people, all that people will be categorized under person without any distinction. Uh, so like person one, person two, person three, that is not there. That is instant segmentation. So semantic segmentation does. In the fully convolutional architecture, sorry, I didn't understand your question, but semantic segmentation fails in any particular scenario. So this is one of the limitation that semantic segmentation has compared to instance segmentation, because you have five people, all of them will be categorized as person, whereas in instance segmentation you have person one, person two, etc. So you get more fine-grained representation there in instance segmentation compared to semantic segmentation. So that is one of the limitations. UNet has an encoder-decoder structure. What does the encoder do? Upsamples feature match the full resolution. progressively downsamples the input, extracting hierarchical features, assign class labels to each pixel, apply stick connection to the input. So the encoder will apply repeated convolutions and pooling all those operations to reduce the spatial size with increase in the number of layers. So the answer is it will progressively downsample the input, extracting hierarchical features, and the corresponding decoder will then upsample this back to the original resolution. The hierarchical is not the same as latent representation. They both do the same, somewhat similar thing, but they are not exactly the same because you extract the features hierarchically. That just tells about the process. So you in the first few layers you extract features like the edges, the corners, etc. And in the next layer, you extract some more higher level features, etc. So that is what we mean by extracting features hierarchically. But then later representation is the final uh, bottleneck representation that is seen after the encoding. So that represents a vector that contains the dimensionality reduced representation of the input. This hyperparameter optimization method explores all possible combination of parameter values from a predefined grid, random search, grid search, Bayesian optimization, and tuning. And so it is grid search that will uh, explore every possible combination of the hyperparameters from the grid. So if you have uh, n hyperparameters and each of them have like say n values, then it will run m into n times to find the best combination in the grid. But then the issue is it will take a long time if the list is very large. How does random search differ from grid search in hyperparameter optimization? Random search evaluates all combination. Grid search evaluates random subset. Random search samples hyperparameter combination randomly. Grid search evaluates a predefined grid of all combinations. They are identical in approach, none of the above. So random set will sample hyperparameter combinations randomly. Grid search will evaluate a predefined grid of all combinations. So if we have four hyperparameters, each with five possible values, how many experiments does the grid search require? 20, 100, 500, 600. Yeah, so each one has five possible values. So 5 into 5 into 5 into 5, which is 625. The F1 score is used to evaluate binary segmentation. How does it relate to precision and recall? F1 is P plus R, F1 is P into R, F1 is 2 times P into R by P plus R, F1 is P by R. Yeah. So F1 is 2 times T into R by T plus R. So this is the precision is true positive by precision is true positive by true positive plus false positive. That is out of how positives that are predicted, how many are actually truly positive, and recall is true positive by true positive plus false negative. That is out of the actual positive, how many are actually true positive. So this is precision and this is recall. So F1 score is a combination of precision and recall. One second. Hmm. അത് അവിടെ പോണം. ഓ, ഒരു മിനിറ്റ്. പുറത്ത് പോവാം. പുറത്ത് പോ. What is the key difference between Savior and naive initialization? Savior uses uniform distribution, naive uses Gaussian. Savior maintains variance across layers based on fan-in, fan-out. Naive uses a fixed standard deviation. Naive is better for deep network. Savior causes gradient issues. Savior samples from Gaussian and naive initializes weights uniform. So in naive initialization, you usually assign some random values. So it uses a fixed standard deviation, whereas in failure initialization, the advantage is that if you take into consideration the number of inputs and also the number of output. So it maintains the variance across the layers based on the number of input and the number of output. So I think the difference between Savior and me that Savior maintains the variance across layers, whereas me uses a fixed standard deviation. It's like Savior will draw from a distribution with the variance 2 by the number of input plus number of input. Whereas in the naive, regardless of the layer, width or whatever it is, it doesn't take into consideration any of those parameters, but it just randomly draws uh, values for weight initialization from a specific distribution with a specific fixed standard deviation. So which can work or which may work very poorly for certain neural networks. Z-score normalization, how is each feature transformed? It is scaled to 0, 1 by subtracting minimum and dividing by range. Mean subtracted and divided by standard deviation of each feature, divided by maximum value of each feature, multiplied by a constant scaling factor. So here we subtract by the mean and then divide by the standard deviation. So if x is the input, then it is x minus mu divided by sigma, where mu is the mean and sigma is the standard deviation. So it is mean subtracted and divided by standard deviation of each feature. Why is data normalization important? When features have very different scales. So for example, there is a feature x1 which has values between 1 to 1000, and there is another feature which has very high range value, like around 10 raised to 6. It reduces the number of parameters in the model. It automatically selects the most relevant features. It removes outliers. It prevents features with larger ranges from dominating gradient updates, leading to more stable optimization. So when features have very different magnitude, then it will affect the gradient update. So more important might be given to features with very large value. So normalization would make all of them be treated equally. So the answer is it prevents features with larger ranges from dominating gradient update, leading to more stable optimization. So in week two, there's discussion about sorry, not in week two, week 12. There is a discussion about surrogate model. So one of the most important type of application of machine learning is the surrogate model. Uh, so one important question. So how to understand this is to start with a uh, very important simple question like when a physics-based model, when it is very slow to compute, or in some cases when it is very impractical to run repeatedly, what do we do? So in the lecture video, they talk about when we have actually a very complex physical equation that govern the atmospheric behavior. So if you run this equation to completion, we can get a prediction. But this will require a large amount of computational resources and also a large amount of time as well. So, if we have to run hundreds of such simulation, uh, then it is not at all like computationally tractable to run such a model. So this is where we use a surrogate model. A surrogate model is like an approximate model, and it is built using some prior computation, some prior experiments. So you run this expensive simulation a number of times, collect some data from this simulation that is run for some time, and then you train a neural network on that data. So once trained, the neural network then can produce answers very quickly for the new input, acting as like a replacement for the expensive analysis. So surrogate models, they are probably the most widely used application of machine learning. Whenever there is a computationally expensive process, especially this is applicable in aerodynamic simulations, finite element analysis, chemical process. In all those areas where there is a requirement for a large amount of computationally expensive process or simulations need to be done. All these areas, they use this concept of surrogate models. Uh, So then they talk about some examples, such as this inverse problem and the forward problem. So in physics problems, you take the reason from cause to effect. So if you are given a set of input, the sh- the shape of an airfoil, for example, the viscosity of fluid or the temperature, we compute the output. So given some input, we compute the output. That is the forward problem, and inverse problem will be in the other direction. So we have a measured distribution of temperature can be determined what are the boundary conditions or some other examples where we go from the output to the input. So this is the inverse problem. This is what usually arrives mostly in uh, many of the applications. So they say that surrogate models can be used to solve those inverse problems efficiently. Um, so a third type of application, this involves a situation where we know the input We know the output, but we don't know what is the connection between them or the mapping between the input and the output. So in some cases, the system is too complex to model accurately, and there are only these many variables that matter, but we cannot write down the equation that drives the input to the output. So, in such cases, a neural network can be used to learn the mapping directly from the data. So, this is called as a data-driven modeling or a learning unknown this problem. So again, then talking about solving differential equation, that is another application. So you can use neural network to directly solve differential equation, both the ordinary and the partial. Uh, so actually, this idea here is not to build a surrogate, but to uh, do the act of solving a differential equation as an optimization problem, and then let the neural network minimize the loss that encodes the equation itself. So the neural network should come up with a minimized, the neural network should come up with the encoding of the equation by minimizing the loss function. Now, coming to, so then they discuss about few of the application, uh, like the heat transfer. So about the thin heat transfer, it is simply an extended surface. You see things everywhere at the bottom of motorcycle using computer processor, etc. So this is mainly used to increase the surface area uh, exposed to surrounding cooler fluid, usually the air, and you want the help. So things in short will help to make things cool down faster. So there is a physical question, like if we have a fin of a certain geometry attached to the base that is at some elevated temperature, how does the temperature vary along the length of the fin? So this is the temperature theta V. So as you move from the base towards the tip of the fin, the temperature will drop. So there is this equation, all this thing given about this problem, and then there is a data set for this problem. Now the solution is to use a simple artificial neural network. There is the input data is represented on tabular, so you can take three numbers and one output should come out. So this is one application of it, and another one is in computational fluid dynamics, where you use the you have a numerical simulation of fluid flow. So it's there in every engineering domain, aeronautics, automotive design, blood flow modeling, etc. So you use CFD in all those applications, and and for most fluid flow, the governing equation is this Navier-Stokes equation, and this is derived from three conservation laws. And for a two-dimensional incompressible flow, the unknowns are the velocity in the xy direction and the pressure P. So this Navier-Stokes equation, this is a set of coupled nonlinear partial differential equation. In general, there are no analytical solution to this equation, which is why the entire field of computational fluid dynamics still exists. So we solve them numerically. So the idea is to replace the continuous differential equation with a set of discrete algebraic equations. So then there is a set of explanation regarding that. So the question is, the ML problem here is, can we train a neural network to predict the flow field without running the full CFD simulation? So if we have done hundreds of CFD simulations in the past, can the 100 and the first be replaced by a fast neural network prediction? So in other words, it's like asking, can we build a surrogate model for CFD? If such a model could achieve, like there is a 2% error when it runs for 200 times faster, it would be having a very enormous impact. But this is something that was already like attempted by few researchers. Um, Now coming to another uh, is this topology optimization. This is the process of finding the optimal distribution of a material within a structure subject to certain design constraints such that an objective function is maximized. Now coming to the another application, which is solving the partial differential equation and ordinary differential equation with neural network. So this does not involve building a surrogate model, but it does not it does not require a training data set in the traditional sense. There is no labeling, no classification, no pre-collected data to learn from. So it just treats the problem of solving a differential equation as an optimization problem, and it uses a neural network as a function being optimized. So the result is a neural network that after training will give you the solution to the differential equation directly. So this idea, it came from a series of papers in the early 1990s and 2000. And in 2019, there was a particularly impressive modern implementation that is that was published by two of the researchers from Brown University. So this is what we call as the physics informed neural networks, or PIN. So these are some of the applications that are discussed. So now coming to some of the previous year assignment questions. Mm, Which of the following is the key advantage of surrogate models over conventional high fidelity models? So they provide more accurate results than high fidelity models. They require significantly less computational time. They are easier to develop from scratch. They always capture all physical phenomena accurately. Yes. So they require significantly less computation time. So in the solution, which will be uploaded, so that in that they explain that the surrogate models, they are designed to approximate the behavior of high fidelity models while being computationally cheaper. Their primary advantage is efficiency as they trade off some accuracy for significantly reduced computational cost. But these high fidelity models, they are more accurate, but they are computationally expensive, making a surrogate model preferable for tasks like optimization and uncertainty quantification. So they require computationally less time. When is it most appropriate to use a physics-informed neural network? instead of a traditional numerical method. When the physical system can be easily solved with standard numerical techniques, when there is abundant labeled data available, when dealing with inverse problems with limited measurement data, when the governing equations are linear and well understood. Yeah, so when dealing with inverse problem with limited amount of measurement data. So in PIN, what usually happens is uh, the neural network will act as a surrogate for the true physical solution. So the physics equation, they will be used in the loss function, and so you compute the derivatives of the network output and you plug them to the partial differential equation, and then you penalize the violation. So the physics equation mainly are used in the loss function and they are not replaced by anything. So by incorporating physical laws into the loss function, things can leverage non-physics to compensate for limited data. So this is what is given as an explanation in the previous year assignment solution. So traditional methods often require dense discretization or are ill-suited for inverse problem without heavy regularization. So when dealing with inverse problem with limited amount of measurement data. In a PIN formulation, what is typically included in the loss function? Only the mean square error between predictions and training data, only the residual of the governing equation, the combined error from data fitting and equation residuals, the error from a separate validation set. So the loss function in PINs, it combines two terms. One is the mean square error between the prediction and the observed data and the residual of the PDE evaluated at the collocation point. So it will include both the uh, data fitting error as well as the residual. So the combined error from data fitting and equation residuals. What technique is commonly used in PINs to compute the derivatives of neural network output with respect to its input? Automatic differentiation, finite difference approximation, symbolic differentiation, manual calculation of gradient. Yeah, so for pins, automatic differentiation is the main thing. I'll just read out what is written in the previous year assignment solution. So it efficiently computes the exact derivatives by leveraging the chain rule through computational graphs, unlike finite differences, which is approximate, or symbolic differentiation, which is computationally expensive for complex networks. So automatic differentiation is implemented in frameworks like TensorFlow, PyTorch that enable seamless gradient computation for PDE residuals. So the technique that is most commonly used in PIN to compute the derivative is automatic differentiation. Which neural network architecture is typically employed for standard PIN implementation? Convolutional neural network, recurrent neural networks, transformer networks, feed-forward neural network with multiple hidden layers. So standard physical neural network, they uses feed-forward neural networks with multiple hidden layers and activation functions like damage, sign, etc. FNNs are chosen for their universal approximation and simplicity. Uh, CNNs, RNNs are specialized for their grid structure or temporal data, while transformers are an overkill for most PDE problems. So it's mainly the feed-forward neural network with multiple hidden layers that is used. In the context of things solving a time-dependent PDE, which of the following statements is correct? Time is treated as an additional input dimension to the neural network. Time cannot be handled directly and must be discretized before using pins. Pins can only solve steady-state problems, not time-dependent ones. A separate neural network is required for each time step. So for time-dependent PDEs, the time is treated as an additional input dimension. So the time is So the answer is A, where time is treated as an additional input dimension to the neural network. Which of the following describes a key challenge when implementing pins for complex fluid dynamic problems? Pins cannot handle nonlinear terms in PDE. It balances the weights between data and physical losses. Pins require explicit time stepping. Pins cannot incorporate boundary conditions. So, one of the key challenges in balancing the weight between the uh, data and the physical losses. The physical loss is the residual and the data loss is from the mean squared error. It might differ by orders of magnitude. So it can lead to, if we take the weights poorly, then it can lead to one-term dominating, causing training failures. So balancing the weights between data and physical losses is the important factor. Which statement is true regarding the generalization capability of pins? Pins can only solve problems for the exact geometry they were trained on. Pins can generalize to different boundary conditions but not different geometries. things trained with physical constraints often generalize better than pure data-driven models. Things cannot generalize outside the range of training data under any circumstances. So, things trained with physical constraints often generalize better than pure data-driven models. So things they say generalize better than purely data-driven models because the physics constraints acts as a regularizer embedding the domain knowledge. However, the generalization is limited to the functional manifold defined by the PDE. A PN, a thing that is trained on Navier-Stokes can generalize to unseen flow parameters, but not to entirely different physics. So, altogether, I think I tried, so yesterday and today I was trying to uh, go through some sample questions from all the weeks together. Uh, and so I hope I have somewhat covered all the questions from the different weeks. I hope it will be useful for your exams. So yesterday's and today's videos, you can check to see those questions. Uh, uh, so I wish all of you all the best for the exam. Uh, so I hope you all prepare well and it will be easy for all of you. Yeah, whatever I have discussed will be uploaded in the folder and the link can be found in the Excel sheet. And also the videos will be available. So yeah, and thank you all for attending all these sessions.